See, so to solve this question, you first have to understand that 0, 0 or 1, 1 are included, meaning that it can start from anything, 0 or 1, as many times as you want. This knee star basically means you take either one of this or this, and then you can just repeat the whole process again, meaning you can make a 0, 0, 0, 0 as many times as you want, and then a 1 as many times as you want. You can go back and forth, and you can just decide not to do anything. But here you are locked. You must take either 0, 0 or 1, 1. We always look at the question and say 0, 0 or 1, 1 are included. So there's an or in between, meaning that you have to put an or in between, and 0, 0 or 1, 1 are included in consecutive sequence. So 0, 0 is in a sequence, or 1, 1 is in a sequence. And then you can just end with whatever you want after that. So given that 0, 0 or 1, 1 is included, we have paths. So we made a path for 0. For example, 0, 0, we made a path like this. And then we made a path for 1, 1. Then when you want, you can only start saying, okay, I'm on the path of 0. If here I can, so considering here, I can read a 0. Where should I go? I should make sure that I can force the path of 0, 0. So if I send a 0 here, it reads another 0 and accepts. That's exactly what I want. So if I send a 0 on this path for 0. So this is path for 0. And this is path for 1. That's why you make two different paths, because they are going in two different directions. 0, 0 or 1, 1, both can be accepted. So if you only decide to do 0 and 0, you get accepted. Or if you only decide to do 0, 1 or 1, 1, you also get accepted. But in this position, you are sending 1 here. You need to send 0 somewhere, the different digit. So because you already sent 1 here, now you have to send 0 somewhere. You can only send, when you send it in this position, what happens is that you force a 0, 0 on the path of 0, which actually makes sense. And if you put a 1 here, it forces 1, 1 on the path of 1, which actually makes sense. Then you have 1, 1, and 0, 0 or 1, 1 are included in this DFA perfectly. Then we have saying that at least 1, 1 and 1, 0 are included, meaning that at least 1, 1 and 1, 0 are included. This leaves us with only two possibilities, just like that, saying that either one of these are included, meaning that you can do whatever you want in the beginning, and then you can do 0, 1, 1, 0 as many times as you want. Not actually as many times as you want, because you either select one of these, meaning that you either select this or this. But still, 0 and 1 is included. At least 1, 0 and 1, 1 is included. So this is included. Even in this, at least 1, 0 and 1, 1 is included. And then you can just do whatever you want after that. What it means is that you make a path again for 0 and 1, and then 1 and 0. See, these are the two paths that you make. Meaning that if you take a 0, you take another 1 like this, and then you get accepted. You make a 1 and you make a 0 and you get accepted. And if you want, you just like back then, we were forcing the path. So we always try to force the path. And back then, when we try to force the path, we try to force the path of 0, 0. So if you go here, if you take a 0, it doesn't make any sense if you come here, because you're disturbing the path of 1, 1, 1. So this is the path that is supposed to make 1, 1. If you take a 0, then go back here and read it here. If you read a 1, then go back here and make the path of 1. That makes a lot of sense, because we are forcing the path. And then we say, okay, reading a 0, read another 0 and get accepted. That's exactly what we want. And that's the same thing what we did here. If you read a 0, read a 1, this is the path for 0, 1. We can even write that. Path for 0, 1. This. And this is path for 1, 0. See, you can clearly see that 1 and 0 and 0 and 1. And that's the minimal idea behind it, to design it for the minimal and then force it on it, force the pattern on it. So now it says that it contains an even number of zeros or an even number of ones. So pay closer attention, that even number of zeros or even number of ones, meaning that it's either even number of zeros, so even number of zeros, or even number of ones. So both of these could get accepted. Either one of this needs to be even. Meaning what we can do is that we can first decide on a regular expression that where first 0 is even and 1 is even. So contains an even number of zeros or even number of ones. So either one of this. Here we design something where we must have even number of zeros. 1 doesn't matter in this position. 1 doesn't matter. Even number of zeros. 1 doesn't matter. As many. So we lock a position where we repeat, and then after that you can have as many number of ones as you want. Then see, we locked even zeros. Even means multiples of 2, and by this you mean you can also not decide to take it at all, and you can just take as many ones as you want. Even and you don't want 1 at all, that's also fine. But if you take this bracket, you must make 2 zeros if you take it. If you don't take it, you can just do nothing, and nothing also means even zeros because 0 is also even. And given that, you can just make even a single one with this, and that means no zeros, and that's also even zeros. But every time you choose this bracket, you must take this after as many times ones as you have taken, or an even number of ones. So here the zeros don't matter. The user can take as many zeros as he wants, and then a 1, because we are making 1 even, so there are just 2, and every multiple of 2 is even. So 2 again, there will always be 2. For example, there's an asterisk here, meaning that 0 is as many times as we want. 1 is only 1. Then you cannot finish here. You must finish the bracket, meaning you can do this many times, and you must do 1 0, and then you can run the bracket again if you want. But even if you run it again, or you decide to run it again, you still must have here 0 don't matter. So that's why it says or, and this is why we understand that it will always be multiples of 2 ones in this situation. Now if you were to design a DFA for it, we see EE here. This is a counter for 0, this is a counter for 1, and we make like this as an accepting state. Then we go here and we say OE and we accept it. Then we go here and then we say OO, and then we go in this position and we say EO. For now, once you made all of these states, of course there are 4 possibilities now. There are 4 possibilities where 0 will be even, 1 will be odd, 1 will be odd, 0 will be even, 0 will be even, 1 will be odd, 0 will be odd, 1 will be odd. So there are only 4 possibilities here. And even odd questions with 2 digits, there are always 4 possibilities. Considering that, when we have, of course, in a DFA, a transition going everywhere. Once you have made this, you can mind map in your head that +1 makes a +1 and a 0 will make an odd, because we're just plussing 1 here. And if you do +1 in 1, it makes an odd. Or if it was already odd, it will make it even, a +1. It will convert it into even. So that's the same thing for both of this. If there was a +1 in 0 and it was already odd, it will become even. Given here, if you do a 0 here and you go there, just look at the 0, it becomes odd. It changes. Now, if I was to read a 0 there, of course it makes sense because that makes it odd. But in case if I do 1 here, it's becoming odd. Because see, this is supposed to change. The other digit's supposed to change. The first is already changed. The other is supposed to change. That's how it got changed, because you read a 1. This is the counter for 1. How did 1 become odd when you only make +1 in it? Only then it's going to become 1. And from here, you can say, okay, there has to be a 0 because see, 0 is changing here from here. So if you do a 0, it goes there and it becomes changed. From here, if you read a 1, it goes here, and you can clearly see that O is changing. 0 remains unchanged, and the 1 is changing. So that's why, see, you can see this, for example. See this and see this. So reading a 1, of course, that's how we know where we have to read a 1, because that's the only thing that's changing this part. And we read a 1 here. Then we read a 1 and we go back. That basically changes it back to normal, back to even. And that's the same thing for here as well. O becomes odd here when we go back. And looking at 0, 1, 1 needs to go back. You can always put 0, 1 here whenever you write these states, so that it's easy for you to map what is changing. Now look at E, and if you go back here, what is changing? 0 is changing. So you read a 0 and you go back. That's how you create a DFA for this. And how would you know that which states are accepting and which are not? You would know that by understanding that 0 is even, 1 is even. So here 0 is even, here 0 is not even, but 1 is even. So it says 0 is even or 1 is even. So either one of them being even is okay. We can check either one of them being even. So both of them are even, of course. Either one of them, of course, are even. Either one of them are, of course, even. And none of them is even, so that's not accepting. That's how we do it. Now it says that, now considering this question as a fact that the number of the word has the number of ones is divisible by 3, meaning that we do not care about the count of zeros. There can be as many, but in that the number of ones is of course not consecutive, but they are at least divisible by 1. They don't have to be consecutive one after the other, but the count of the words of ones needs to be divisible by 3. So you can start with as many zeros as you want and then finish there because of this, and not start this bracket at all. And 0 ones is also divisible by 3. So including 0. So 3 in all divisible questions is the same. 6, 9, and so on. It's the same. Now, once you do this, you realize that you can do as many zeros as you want, which makes sense. It can start with whatever zeros, but it must have a 1, and it can do as many zeros, and then it must have a 1. It can do as many zeros, it must have a 1, and then repeating that bracket. Then, of course, it can start with as many zeros right now, but if we give that option here as well, it will just doesn't really matter, right? Because you already completed the iteration. You already have the number of zeros do not matter, but the number of ones must be divisible by 3, and that's what all matters. And if you do this, you will always have a number of ones that will be divisible by 3. Considering that, making an DFA for it would be quite easy, because all you have to do is you have to make states that make the divisible by 1 possible. For example, try to make the minimal state. We see these 3 ones in a stack. So Q1, Q2, and Q3. Considering that, you make a 1, and you can make the third one actually going back to its own, like this, like a loop. Third one, like this. And in that way, 1, 1, 1 will be looping on its own. It can start with as many zeros as you want, and no ones at all. It can read no ones at all, and this can be our accepting state, because it didn't read any zeros and it just got accepted after reading a 0, and that's fine actually. But then when it goes and reads a 1 and goes ahead and reads another 1 and 1, only then it can complete first loop. So if it decides to go in this direction and go ahead, it always needs to do 3 ones, and then it will be completed. It cannot finish here. If you want to finish here, you can do as many zeros as you want, and here you can do as many zeros as you want, but still see, you must go ahead with this arrow. You cannot stop here. And it's the same thing as this, that in the beginning you can have as many zeros as you want, and in the end you must have to move forward like this. To move forward with this arrow, you always need to have a 1, and to complete the cycle, to get accepted, you always need to read 3 ones in a cycle. And then if you want to repeat the cycle to move forward, this DFA will always have the number of ones that are divisible by 3, because then you can just decide not to do anything here. Or if you want to move forward, then you must read 3 ones in the whole word again, no matter how many zeros are in between. See carefully. It says that contains at least one A and at least one B. So 1A and 1B, like this. These are the two options. It's the same question as we had before, at least 1 0 and 1 1. These were the two possibilities that we were left with, right? It's the same exact thing. In that way, we know that at least 1A and 1B are there. These are the two possible combinations that we are left with. And both of them, for example, that can at least 1A and 1B. So these both would lead us to the same outcome. Meaning, first let's try to make a regular expression for this. It says we have A, B, or C in the word, of course. Then we can, because you can look at that. But there's nothing about C that we have to be careful about. But we have to lock, there's a condition about A. Let's first make a path for AB. Then A, B, as many times of that, but you must read a B. That's included in the word. Then A or B or C as many times as you want. Or you do or in between. You do A or B or C as many times as you want. Then you do, I think it would be good if I do the or with this. This is an or in between. B, A. As many times of B's and C's in between does not matter. A or B or C as many times in between, it does not matter. And an A. That's the part. These are the two possibilities. So you either take this or you either take this. And both of these paths that you take will guarantee that you have at least one A and at least one B. Both of these paths will guarantee that, because there are only two possible options. Then we will go on with the same approach. At least one A and one B, meaning AB and BA. Let's make a DFA for it. And of course, just like we learned in the past, that if we do a Q0 and we go here, we do Q1, we do here, we make path for AB first. This is that. Q3. Then we go and make a path for BA. So A, just put AB there and put BA here, because this is the path for that. Path for AB, path for BA. And for the second arrows, you could just think about what will keep the path of AB, what will keep that AB there and not destroy AB. Here I can send an A somewhere. Where should I send that A? I can only send an A because I already sent a B somewhere. I can send an A here, and that basically promises that we will have A, B. So I'm forcing the path of AB. And here we have a BA, and how do I do that? This is the path of BA. If I can only send a B here, but why should I send a B over there? That is the path of AB. I can send it here, and then we have BA. And that's the path for BA actually, right? just like I said, this is BA, and that makes BA possible. If I was to send B there, it basically destroys the path of AB by making AB B. That's not what we want. We want to make AB, and that's why we send B here. That makes BA. Even if it's like that, it's still BA. Considering that, we are still left with C. On here, we can just send C on its own because C basically has no value in our question. We don't need to do anything with C. And in here, we already send a B. We can send C here. We already send A. We already send B. We can send C here. And here, it doesn't matter what you do. You can do A, B, and C. Why? Because you already got accepted. You already completed your word. So in here, it doesn't matter. Considering that, you must understand that it's trying to say that contains at least one pair of consecutive ones. And what that's supposed to mean is that it's the same thing as trying to say that it contains at least one pair of 1 1. 1 1 is, it contains 1 1. So 1 1 is included and it's consecutive. So basically 1 1 is included at least one time, meaning that it can start from anything. It doesn't matter. We lock 1 1 in a consecutive way, and then it can have whatever. It doesn't matter. And to make a DFA for it would just basically be so easy, because all it needs to have is a 1 and another 1. And anything that goes, so whenever you make contains questions, you see things like this. It could start with 0, but it should have 1 1. Could start from 1 and could have whatever. So we already gave a 1 there. We can only give a 0. It will satisfy this condition here. Then from here, we can only do a 0, but I cannot send 0 anywhere because it will just destroy. If I send it here, it will not let me do 1 1 consecutively. It will let me do 1. It will allow the user to do 1 0 1, and we don't want the user to allow the user to do 0 here. Then I send it back because I want to lock it. 1 1 is locked. To move forward, you must do 1 1, and here you could just do 0 and 1 as many times as you want, which is our accepting state here. So basically in this question, it tells us that all pair of consecutive zeros occur before all pair of consecutive ones. So all pair of consecutive zeros occur before all pair of consecutive ones, meaning that this is right. So all pair of consecutive zero occur before all pair of consecutive ones, meaning that any pair after the 0 is not possible. For example, 1 1 0 is still possible, but 1 1 0 0 is not possible. So in these questions, maybe try to look for what's not possible. Whenever you try to look for what's not possible, most of the time you really understand that. It's basically, this question is in disguise, that 1 1 is not possible. And another time the question might say that does not occur after 1 1 has occurred in the word. So 0 0 does not occur after 1 1 has occurred in the word. This is much more clear way to say it, that 1 1 0 0 is not allowed. Of course, because if 1 1 has occurred, the 0 0 is not allowed. So it does not occur after the 1 1 has occurred. So 0 0 will not occur after that. This is another way of writing the same question, but again it means the same meaning that we know. Now considering all of this, we can understand that we can try to make a regular expression for this firstly, but considering that, we have to understand this basic phenomena that we can convert it into 3 phases, for example. So for example, if you look at phase 1, we look at 0, 1, 0, meaning that the first phase, we can design it this way, that in the phase 1, basically we want to achieve that the word does not contain 1, 1, 0, 0 is not. So the first phase 1, will not have 1, 1, meaning what we can do is that we can lock it in this way, 0 or 1, 0 as many times as you want. But in this way, with phase 1, you can never make 1, 1. Why we do it? We do it because then we can always make 0, 0, 0, 1, 0, or 0, 1, 0, or 1, 0, 0, or 0, 0, 1, 0 with this 0, 0 again and then 1, 0 again. But 0, 0 is allowed, of course, but 1, 1 is not. Because see how always 1 is concatenated with a 0, and it always finishes with a 0, right? But in the second one, here it's a phase 2, where we can say 1 or 0, 1 as many times as you want. Okay, and in this way, with this, you can then design 1, 1, a single 1, of course, 0, 1, 1, 0, 1, 0, 1, 1, and 0, 1, 0, 1, 0, 1, 0, 1 again, as many times as you want. So here 1, 1 is allowed. And in the next phase, we will be smart because we will only give 0 as a whole. We won't give 0, 0 and then epsilon, nothing. You take a 0 or you take nothing. That's the only way we guarantee that this phase guarantees no 1, 1. This guarantees no 0, 0. And this guarantees, if you want, you can just take a single 0 if you want, which limits us with 1, 1, 0 and all other combinations. Considering a DFA for this one, I came across with the easiest concept that you have to keep in mind that it does not contain 1, 1, 0, 0. Meaning, first try to make a contains one. For example, contains 1, 1, 0, 0. How would you do it? You would say, okay, 1, 1, 0, 0 it contains. So you say 1, Q1, Q2, Q3, and Q4. 1, 1, 0, 0. It contains 1, 1, 0, 0, right? And then it's accepted. Meaning what happens is that if you try to read and break the pattern of 1, 1, 0, 0, you need to go back. Of course, whenever you make contains questions, you always consider 0 or 1, 1, 1, 0, 0. So 1, 1, 0, 0 is possible, but here, if you can only give a 0, and that makes sense to just loop it here. If you were to take a 0 here, you will break the pattern, sending it in here, then why not just send it back? Because we locked a 1, 1, 0, 0. Then 1, 1, 0, 0 will not be in a sequence. We want this in a sequence. Then in here, if we were to send, okay, now it gets tricky, because if we were to send a 1 back there, it can go back again and then take another 0, and then it will make 1, 1, 0, 0. See, let's try. If you make a 1 here, you have to be careful in every iteration. If you make a 1 here and you go back, then basically, so first of all, we were clear what we have to do in the question. 1, 1, 0, 0 not. It does not contain 1, 1, 0, 0. Once we know that, it's just easy from that. We created a question for contains 1, 1, 0, 0, but we make sure that from that we have contained, it does not contain 1, 1, 0, 0. That's our final goal. So we can already move forward to our final goal. And that would be, in this position, if we send it back 1, 0, 1, so it could possibly make 1, 1, 0. For example, 1, 0, 1, 0, 0, 1 here, 0, and 1 again. So for example, 1, 1, 1, 0 1 1 1 0 0 1 1 1 0 0 1 0 1 1. See, 1 1 0 0, we made it with this, what we were doing. You get what I mean? 1 1 1 1 1. So we only consider the last two ones, and then 0 and then 0 1 1. So we accidentally made 1 1 0 0, but we're not supposed to do that. And that way we can just send it on its own. Meaning, if we send it on its own, then you can just loop here and make 1 1 1 1 1 0, but the moment it goes here, it doesn't stay accepting anymore. That's the knot of an accepting state, is that all of the others are accepting, and we'll come back to that later. How does that work? How does that work when you can make something like that? How does that work? This also becomes accepting, this also becomes accepting, meaning that 1 1 0 0 is just not possible, and everything else is possible with this, because I just made contains 1 1 0 0 and I created a knot of it, and I made sure that that knot works. Plus, all of, if this was a contains question, then this becomes an accepting instead, but I inverted all of the states. This is also possible. So every possibility of 0 but no 1 1, and every possibility of 0 0. This is for this statement that I explained. So now focus how important it is that all strings of zeros and ones whose, so the set of all string of zeros and ones whose number of zeros is divisible by 5. So here they say that 0 is divisible by 5. Okay, which meaning it's the same similar question as we had before back then, and it basically wants us to understand that the number, it's basically the table of 5, meaning 5 10 15 etc and so on. So these are divisible by 5, including 0. So any number is divisible by 0, of course, and moving on with 15 20 and multiples, meaning that every single loop will look something like this, that as many number of ones we have, it doesn't matter, but we lock a 0. Why? Then I tell you, then as many number of, then we lock a 0. We can of course do it like this. First make another one, or maybe do it like this, that 1 2 3 4 5. We already have 5 zeros, it doesn't matter here what's here, and then we put like this, and then we put an asterisk here, meaning that it will always have 1 2 3 4 5 zeros, and it will loop on its own again and again. Every time you use this, you will always have multiples of 5 zeros every time, and if you don't use it, it's basically 0 zeros, which also is divisible by 5, so it also makes sense. Let's try to make a DFA for this, meaning what you do is that you start with making a Q naught that goes to a Q naught that reads a 0, another 0, another 0, 1 2 3 4, and the fifth one back here, loop on its own, looping. When it loops, this is the accepting state, meaning that when this is the accepting state, it will always run in the cycle of 5, 1 2 3 1 2 3 4 5, 1 2 3 multiples of 5, plus it will also going to read ones at some point, but whenever it reads a 1, it will read a 1 on its own like this and get accepted, of course, and there's 0 zeros, which is also divisible by 5. Then it goes one step ahead, but here notice that the sequence doesn't matter, meaning you can just do it like this, and the sequence does not matter. You can just do it like this and the sequence will not matter. And you can read a number of zeros that will always be divisible by 5. Here we have 2 arrows, here we have 2 arrows, and we have all 2 arrows. And we have to still move forward. We can have 1, 1, 1, 1 as many times as we want, but to move forward, or if we enter the loop, we will read 1, 0. And if you read 1, 0, it's impossible to get into accepting without actually completing 5 zeros. And no matter what you have in between, you will definitely complete 5 zeros and then get accepted. And this will always loop. Now, considering this question, it says that it contains the substring 0, 0, 0, of course, consecutively, anywhere in the word. Meaning, let's look at the regular expression. It says that 0 or 1 as many times as you want, but then you lock this. And then you say 0 or 1 as many times as you want. But notice how you lock 000. The moment you start this regular expression, you can of course do whatever you want with it, but you must have 000 and then of course whatever. This also coincides that whenever you look at contains questions, we always look 0, 0, 0, and then we say, okay, it should start with 0 or 1. In our case, we can say that it started with, let's try to make a DFA with it, for it. Q naught, very simple, 0. Always make for the minimal accepting. It should be 0, 0, and another 0, right? 0, 0, 0, 0. And from this position, you can read, of course, just like I said, you need to consider these two cases. How are you going to make 0, 0, 0, and another 0? We're going to look at that later, but here you can only give a 1. So, of course, it makes sense to give it 1 here. So, you can start with 1, 0, 0, 0. 1, 0, 0, 0 works. Here, only you can give a 1, but the sequence will be disturbed if you give 1 here. You must give the 1 somewhere else to make sure that you don't disturb the sequence of 1. In that case, you can give 1 here. So you don't disturb the sequence of this 0, 0, 0. If you were to give it here, it would be 0, 1, 0, 0, which is not right. Then, same goes for here. If you did that, then if you did send it here, then you can do, if you send a 1, you can only send a 1 somewhere because you already send it a 0 here. If you send a 1 here, it will just go 1, 0, 1, 0, 0, which is not right. And of course, whenever you make a minimal, always make the final one accept, like the minimal accepting state as accepting. So 0, 0, 0 was accepting in that position. Meaning that if you cannot do it here, that means you have to either send it all the way back to this position. So if you read a 1, you go all the way here and you start again, so that 0, 0, 0 is included in the word. You cannot make a word without 0, 0, 0. It's included. It's like it says that contains the substring anywhere in the word. Then you can just do 1 or 0 as many times as you want. Now it says that it contains 0, 1, 1. Of course, we know that it can start for anything, and it just contains 0, 1, 1. And then it can end with anything, of course. That makes a lot of sense. But then, just like we said that we know for the contains questions, we always try to look for one thing. So 0, 1, 1 is there, 0, 1, 1 is there, but it can start with what? Either a 1 or either a 0, right? Meaning that you could say Q naught goes to Q1, goes to Q2, reading the minimals, accepting 1 and then another 1, right? 0, 1, 1. That should be accepting. That should be our accepting situation. Like this. 0, 1, 1. Meaning that in that case, I have to do something that does not destroy our pattern. First of all, let's do 1, 0, 0. Of course, I already did 0 here. I have to send 1, 0, 1 somewhere. I will send that 1 here so that I can make this. Then I say 0, 1, 1. It contains 0, 1, 1. If I send a 0 here, then think about what keeps our condition. For example, we already read a 0 here, it makes sense to read a 0 here, because then 0 1 1, right? See, 0 1 1, and that makes a lot of sense. This is very important. Whenever you make a DFA, always in every state, think about these things. About when it contains question, think where you are in this position. And when you are at this position and you are reading a 0, you're locking, basically you're trying to lock, and we did this quite many times. Our main intention is to lock this, and to be able to lock this, we don't give any other possibility, which is 0, you do 0, and then you basically, for example, if you did a 0, you did a 0 here, you did a 1, you did a 1. We're doing the same thing we wanted. So we're saying 0 1 1 0 1 1. That's what we wanted, right? Isn't it like that, or is it not? And in that way, we could just send this. Okay, now from here you can send a 0. Where would you send it? Again, come here, 0 1 1. That's exactly what we're looking for. So we're locking in any position that you're just trying to make sure that 0 1 1 is there included. It's not getting away anywhere. And in that way, you just kind of lock 0 1 1, and in the end you can just do 1 or 0 as many times as you want, because it's already an accepting state, so it doesn't really matter. This state is already accepted. So then this is a complete situation. We have consecutive situation going around, mean this is a consecutive sequence. We have to make sure that it's consecutive, and it's the all hands are at the right position where they should be. And if you already give a path, then we make sure that the path makes the word. These things are important. So see, what you do here is that it says do not contain 0 1 1, meaning 0 1 1 is not possible. So it can of course start with 1, as many ones as you want, but notice how in the second block, so we make two phases. The first phase is just as many ones as you want, but in the second phase we will not allow 0 1 without a 1. For example, we will finish with 0 1, of course, but then we will have nothing. But here you can have a 0 if you want, and it's the same thing as this but separated. So for example, and you can put an asterisk on this, wait a minute, 0 1 1, you cannot do that, but you just separated it in a way that you did 0 separately and 0 1 separately. So you either choose a 0 or 0 1, and if you keep going back on this loop, you can do 0 0 1 and zeros as many times as you want, and 0 1, but you will never do 1 1 after it. Notice how a 0 is glued to a 1, meaning this 1 is basically discarded, and the other opportunity is to make a 0. If you give an opportunity to make a 1 here, for example, that would be a problem, because you could just say 1 1 0 1 0 1 1, 1 1. Yeah, you could just say 0 1 and then go and read just 1 1, and that would just make 0 1 1. That's not what we do. That's not what we want. We say this phase basically locks the possibility of making a 1 1, and this forces that you can only make ones. Meaning you can have as many ones as you want, 1 1 1 1 1, but no zeros. So basically it makes sure that you can have ones but no zeros here. And this one basically allows you to not make, because if you were to do 0 0 here too, then you could just make a 1 1 or do a 0 1, and then it would just basically destroy our condition. But then we allow as many ones as we want, and then we don't allow a lone 1 1 here, which locks us with this situation. This is how you distribute a 3-word digit. So it's a 3-word digit by giving it only has 2 possibilities, breaking into those 2 possibilities, and then giving the possibilities of as many ones in the beginning. Considering the fact that 0, 1 or 0. 0, 0, 1 never makes, no matter how many times you repeat it, it never makes 0, 1, 1. It's basically the invert of it. For example, the invert of this would be 1, 0, 0. But it's written the other way. So 0, 0, 1. Like this. But written in the opposite way. And in that way, you can never, even if you loop at 0, 0, 0, 0, 1, you can never make a 1, 1 because I never give the possibility for it. Considering that, a knot for this would be very easy. The DFA. You could just simply take this one that we made for contains and after that, just 1 minute, we have to copy this. Copy this and we paste it here. But notice what we will do now. We will basically turn all the accepting states into non-accepting ones. And in that way, we can easily make this as a knot. Accepting as not accepting. And all of the others become accepting. Then that way you can never make, because the moment it gets here, it doesn't stay accepted anymore. And you can never make that. It does not contain that. And it contains, of course, everything else. So you can make a contains one and then you can just invert it. That's how you make a not contains one. Now let's talk about how you can create a minimized DFA. What you do is you look at S3, considering that S3 is our accepting state, and you make a table for it, looking at A and B, considering states S0, S1, S2, and S3. Now you know that A goes to S2 and S1. You can see this on the table. It reads the A, It reads the A and goes to S2. You can make it like this, SO. This is our accepting state. S1, S2, and S3. Here we know that S2, A reads A on S. It reads A. S2 reads A and goes to S2. It reads. So now what happens is that you just basically write, first of all, there are different states that we have, and then on so state 0 reads an A and goes to S2, reads a B, goes to S1, and state 1 reads a A, goes to S0, reads a B, goes to S3, and state S2 reads a A and goes to S0, reads a B, goes to S3. Then S3 reads a A, goes to S2, reads a B, goes to S3. Now pay careful attention. We know that S3 is an accepting state, so we can already highlight our state like this and say this is an accepting state and this is a non-accepting state. Well, that way we will know the first partition that we will make will be here between P1 and P2, meaning this will be our P1, this will be our P2, between accepting and non-accepting states. Then we just go ahead and give names. For example, S3 is in P2, give it P2, S3 P2, S2 P1. Why? Because S2 is in P1 partition. S0 is in which partition? P1. S0 is in P1. S2 is in P1. S1 is in P1. S3 is in P2. And now what we do from here, for the further partition happens when we try to compare these two here. They are the same, so no need to partition. Wait a minute, that's different. P1 and P2. So we look only at these partitions. They are different. And if they are different, what happens is that they are different, and now we try to create a new partition here and just rename it differently. For example, we might say P1, P2, and P3. And based on that, because we know that these two are not the same, we can just make a partition here. And once we did it, we can see these two are the same, these two are the same, and this does not get divided because it was already an accepting and it was single. Now what happens is that based on all of this understanding, we just change names now. So S0 is P1, no, actually S2 is on partition 2. S1 is in partition 2, so we just change the names afterwards. Here, see, S1 here is in partition 2, and look at here, S0 is in partition 1, that's accurate. S3 is in partition 3. S0 is in partition 1, that's accurate. S3 is in partition 2, that's not accurate. And S2 is in partition 2, S3 is in partition 3, and now we have the minimized situation because there's nothing more you can do after this. You can see that these are, though this is already isolated on its own, compare these two, because there's a partition here, compare these two, and they are the same, right? These two are the same, they go to the same partition, and these two also goes to the same partition. These two, they go to the same one, and this also goes to the same one.